Hey guys, what's going on? So today we're going to be talking about conformal generators. These are really going to form the bedrock of conformal field theory. If you're not aware of conformal field theory, this is sort of the language of string theory and phase transitions, and it plays well with topology also. It's more on the advanced end of things when we're talking about physics, which is kind of why I want to get into it. I've always been interested in conformal field theory, and I've studied it in some depth. I'm not an expert in it, but I want to talk about conformal field theory. I've made a playlist and so forth. So let's just go ahead and get started. So again, if you want exclusive content, then you can go onto my Patreon page and become a member here on YouTube. So in conformal field theory, there's objects called generators, and these things generate infinitesimal transformations that we mentioned in the last video. These generators form an algebra, which constitutes the foundation of conformal field theory. And we're going to talk about that as well in our next video, the algebra. But the essential equation that we're dealing with again is this guy right here, where we're changing space-time coordinates, and the space-time coordinates are changed by a small infinitesimal value, and that is encoded in this guy right here. Last time we got to a point where we were able to show this, and from this equation we were able to beat it up to a pulp to get some useful differential equations out of it, which told us what the form of sigma should look like. Okay, so we're going to beat it up a little bit more, and we're also going to absolve the factor of 2 into sigma, because this is really just a constant, and that multiplies by our metric. And what we'll be able to see then is all the necessary and all the mathematical logical consequences that come from this guy right here. Okay, so the first thing is first we're just gonna contract both sides with our flat metric, and we're dealing in flat space. This also works in general curved space, but we contract, and when we do that, the contraction of these two guys is going to give us the dimensionality of our space. And then this guy here, well, we're just raising indices, these here, and we're going to get two divergences of our epsilon. Okay. All right. So we get we get 2 of them, and then from here to here, we're just divide both sides by d. All right. So plugging 4 and 3 back in, right? So now I've numbered the equations, which is useful for when we start referring back to equations. So I don't have to so I don't constantly have to be searching for the equations I'm looking for. Plugging 4 back into 3, so this guy into this guy, we get this, and this is the equation that we are always going to be referring back to. Okay, so the idea here again is that this is the big daddy equation. Okay. From this, we're going to derive all the necessary generators for conformal field theory. So this video might be a little bit long, but we're going to get all of these guys out. We're going to get the generators for translations, generators for dilations, generators for rotations, and generators for what really makes conformal field theory unique are these special conformal transformations like this. We sort of hand-wavingly established this in the last video as being the solution to a differential equation, but now we're going to actually derive it full force. And so let's go ahead and get started. We're going to start off with the translations. So our aim is to derive all these generators, but first we need to get some useful identities out of this first. So we'll start off with contracting both sides of the equation. This guy here, we're not really contracting, we're multiplying both sides by, or we're taking the partial derivative of both sides, right? And when we do that, I'll just zoom in a little bit, we get this first equation, and then we distribute, right? Distribute, and we get this guy on this side, nothing changes. And then here, this here is called the D'Alembert. The D'Alembert is this guy right here. So these two guys are the same. And again, nothing really changes here. What we're doing here is we're really just we're raising indices, right? or so we're taking new and we're replacing with mu, and we get rid of the metric. And so the metric is raising and lowering indices there. And if you're not aware of raising and lowering indices, that's something that I would refer you back to my on my tensor calculus playlist or my general relativity playlist. And so now we get from here to here then we're just taking the partial derivative again, okay? And then from here to here, we get this guy here, right? Because this guy here is this right here. And then we have a 1 out here, which is this guy right here. Our d-Alembert stays the same. This guy should be a d-Alembert. And then we're not really getting from here to here per se. What we're actually doing is we're swapping mu's with nu's, right? Because they're all just dummy indices. So mu's with nu's to get from here to here. And then from here to here, well, what we're actually doing is I should write this a little bit better. We're adding these two equations together, these two guys. So we swap the indices, add them together. We get this and this. And to get from here to here then, this guy here, well, that is this guy right here, right? And we divide both sides by 2, and we get this here, right? And so what to get from here to here then is just, well, right, so we could see here that this guy here and this guy here is this right here. So we're really just factoring this guy out. And we get this guy here. Or actually, I'll do this in a different color. So these guys are right here. This guy is right here. And then we have 1 minus 2 over d. You can pause this if you want, but this guy and this guy will turn out to give us this factor right here. And so what we get here is this equation. We can contract again. So when we do this, we're contracting both sides with g mu nu. And so we get this guy here. So we have d plus d minus 2. And so what's that? That's d times the d-Alembert plus d minus 2 times the d-Alembert. Well, that's going to be 2 times d minus 2, but we just factor the 2 out. And then from here to here then, well, we just divide both sides by 2. And so we get this guy right here. So these are two very important equations. Let's build one more equation because we're going to need it. So similar to how we build the Christoffel symbols in general relativity, we can do the same with this go-to equation. And so we start off by taking the derivative of both sides of 5, right? So our equation 5, this guy right here, we take the derivative of both sides and we get this, okay? And what we're going to do now is we're just going to interchange. So in this equation, alpha is going to go to mu, mu is going to go to nu, and nu is going to go to alpha, right? So alpha to mu, nu to alpha, right? So nu to alpha, mu to nu, and then in this one we're going to go alpha to nu, right? So alpha to nu, and then nu to alpha, and so forth, right? And then what we're going to do is we're going to add this equation and subtract this equation. And what ends up happening is that these two guys are the same, they will cancel out. And nu alpha, alpha nu, these two guys are the same, they'll cancel out as well. And what we end up getting is this guy right here. Okay, so now we have all the equations necessary to derive the generators for all of the types of transformations that we wish to derive. Okay, so we're going to start off by deriving the transformation generator, or the translation generator, right? So not transformation, this is going to be translation generator. So translation generator. Our translation generator But first we're going to consider this guy the following, right? So really what we could sort of think of this as higher degrees of transformation of this guy, right? So this guy is just the transformation. If this guy and this guy are 0, if these two constants are 0, then our transformation is just a constant. Our transformation can also incorporate rotations, and that's going to be built into this guy here. Dilations are also going to be built into this guy, and then this guy is where our special conformal transformations are going to come from. And you can think, well, what about plus d mu nu rho eta, and then we have x mu x rho x eta. We could think, okay, what about this guy? What's this guy going to do? We could do that, but for right now, let's not. We're primarily just interested in these first 3 contributions to our transformation. So these are like components of our transformation, if you will. We have rotational components, dilational components, translational components, and then the special conformal components, which is what's going to come out of this guy. But let's start off with the translation. So consider the transformation that we had mentioned earlier in our first video, which is this guy. It's clear to see that this guy then is going to be alpha, right? Or not alpha, a mu, right? Because we're saying that if we're going to omit these two guys. Okay, we're going to omit these two guys. We're saying that we're just dealing with the translation. If we're just dealing with the translation, then alpha is what's interesting to us. And so this is our equation then to get from here to here. We're ignoring the effects of B and C, and we'll bring those in later. But so now, well, we could say that through this relationship, d mu nu equals d mu x nu, right? So we're using this to get to here, right? Because this partial derivative, this is going to be, what this is going to boil down to is x1 plus d2 x2 plus so forth. All right, so if we do something like d2x3, well, that's a no-go. That's going to give us a 0, factor of 0. So that's how we can get from here to here. So then from here to here, then we just do we multiply. So minus I times I, well, I times I is -1 times this minus sign, well, that's just going to give us positive 1. So multiplying by -I² does nothing, okay? And then we have the rest here, right? And then what's interesting about this, so why the reason we did this is because now we have identity operator 1 plus this thing here, okay? And so this guy here is our generator, right? Because we have our A new, this is our A, but this thing here is what is the operator that generates our translations. So from this we can see that the generator for this type of transformation is this. Now let's turn to dilations. In this case, we're interested in the second term in equation 9, right? So here's equation 9. And what's going to happen here is that we're going to get dilations and rotations out of this guy. So let's talk about dilations first. So this is our second factor. First, dealing with the right-hand side of equation 9. Again, I'll go back up here. We get, is that equation? That's not equation 9. What I think I meant was this guy right here, equation 8. So equation 8, when we're dealing with that, we want to calculate this guy, right? So let's calculate that guy. That guy is, well, this is just this, and then again, this guy we called up here, and then from here to here, this is just our constants or our matrix or rotation or dilation matrix. We don't know exactly what it is yet, but we can bring that up front. We're taking the derivative of this guy here. We're just calling this a constant for right now, right? So if this is a constant, we bring it out front. And then this guy here, well, that's a metric. And so this then raises our mu index, right? Or our new index. It raises one of the indices, and so we get this. So in terms of this B rotational matrix thing, we can, if we get the trace of it, we can get the dot product between or we can get the divergence of our transformation, infinitesimal transformation. Now we're dealing with the left-hand side of the equation in equation 9, right? So yeah, now I know this actually should be equation 8. Equation 8. No, I changed that too. Okay. So this guy here. So this guy here then. Well, we can plug what we define these two guys as, right? We define them as this guy and this guy, and then from here to here, then we take again, right? So this is alpha nu. Right? So alpha nu. Yeah, so alpha nu here, right? So this guy and this guy. And then this guy here gets out front. And then we do the same thing here for this guy. And then we raise index here, right? So this guy here is just the sum of these two guys. Taking equation 14 and 15, right? So here's 15 and 14 is down here. We can now reformulate equation 8. Equation 8 or equation 9? Let's double check. Yeah, equation 8. Equation 8. We can now reformulate equation 8 to get this guy here. And so from here to here, then, we are just multiplying or dividing by 2. Okay, and so we get this. And so this looks an awful lot like a symmetric part of some matrix, right? So if you're not familiar with anti-symmetry and symmetry, you can, I've talked about this a little bit in my quantum gravity playlist. I've talked about it a little bit in my tensor calculus playlist as well. But this looks something like the symmetric part of some B matrix. And so this is to say that the matrix is proportional to the metric tensor, right? Because the metric tensor is on one side multiplied by some constant, because again, this is just a trace and this is just a number. So it's proportional to the metric. But if we want to be complete, we can add on this anti-symmetric part as well. So if the anti-symmetric part is 0, then we can say that our transformation, well, if it's this guy again we defined in this way, but this we defined as transforming as proportional to the metric. And so from here to here, then we're raising and lowering indices, and we get this guy right here. This is dilation. This is our dilation transformation, and from here we get this equation right here. And so this equation right here is going to give us this right here, right? Because this guy, as we've said, we can replace with this. And then we're doing the same thing as we did with the translation. We went to go from here to here, then again multiplying by, to go from here to here, we're multiplying again by minus I squared, which does nothing. And so we have our identity operator plus our dilation part. This is our generator then. Right. Okay. So, and I'm realizing right now there should be another parentheses there. And so our dilation generator is this guy. All right. Let's go move on. Stretch. And let's keep on going. So when the anti-symmetric part of the matrix is not 0, however, and the symmetric part is 0, we can get rotations. And we see this by doing this guy now, right? So our M matrix contains the anti-symmetric part, and so we can raise in an index in like this, because again, it's just the matrix part, and so it's just a matrix, and so from here to here then, from here to here, we have, we can sum over alpha, right? And then we replace this guy here. So we're really just inserting and adding a new, we're adding a new index. And then so from here to here then, we get, we're using this anti-symmetry property of this M matrix, right? Where we have this 1/2 of this minus 1/2 of this. And then from here to here, then we're taking this guy out of the equation. We're taking this guy out of the equation, and we get this here, right? So because this right here is this guy, and this guy right here is this guy. And so from here to here, then we get, or from here to here, we're multiplying by I, right? And that should be a minus I, right? That should be a minus I. And then we have from here to here, to get from here to here, we have we're absolving the 1/2 into our matrix, and so this really is what our generator looks like, is this guy, because now we have, again, unity or identity operator plus all this guy. This is our rotation matrix, and this is the thing that's generating that rotation matrix. Okay, so now we have the generator for rotations. So we have our generator for rotations, dilations, and translations. Our B matrix therefore contains all the information about dilations and rotations, and so that's this guy right here. So now we turn to the third term in equation 9. So let's go back to equation 9 really quick. This is going to be this guy. So this is where we're going to start talking about the special conformal transformations. Special conformal transformations are going to be interesting. So let's start off. So we define epsilon to be now this change, and with these c constants, so we take the c constants out in front again, and in this case here, mu nu, right? So let's see, what did I do here? This is alpha nu. Here, so here's our alpha, and here's our nu, here's our x nu. So let's see, this guy is this guy right here, right? So this guy here is taking the derivative of x alpha. So we have mu alpha, and that's the mu alpha right here. Okay? And then mu nu, that's this guy, or this guy here multiplied, right? So, okay, the point here is that we have, what we're actually doing is we're saying that d mu acting on some vector x mu, well, that's going to give us, that's going to be the same thing as our metric mu nu, right? And it's a little bit not obvious here, the way I typed it out, but we can see that when we use this guy, we're getting these metric tensors in here. This is the product rule. You could sort of think of this as the product rule, right? Or it is the product rule, right? This is the product rule because that these two things are being multiplied by each other. So let's just write that product rule. Product rule. And then from here to here, then we're using the metric to raise indices. And then from here to here, then we have mu mu alpha, x alpha, c. Okay, this is a little bit messed up. We don't have four indexes, we don't have four indices. We're just changing the order of these indices, and we can see that these two things are really just the same thing. So, which is why we have two of them. So we have this equation here. We'll call that equation 24. And let's move on. So we can also note this here is given to us epsilon again. We put epsilon here, and we're doing sort of the same thing, right? So rho nu, or rho mu, beta nu, right? So rho mu, beta nu, rho nu, beta mu, So these guys and these guys are what give us this guy. It's sort of the same principle of what we did before. Or it is, right? I keep on saying sort of, but it's the same principle as we did before. And so, again, this is just raising and lowering indices. So we raise and lower indices now. So we have mu nu, here's our mu nu, rho beta. Same thing here, rho beta, nu mu. And then, so these two things are the same thing. And so we get 2 times c alpha mu nu. Okay. So now we have, so that we'll call this equation 25. And so if we take 25 and 24, then again, 24 being this guy here, we have this guy here. Again, my apologies for the dog. And we put him back into equation 8, right? So going back to equation 8 is this guy. So we calculated this thing and this thing now. Now we're going to put it back. All right, so this guy and this guy. And the 2 went away because there was a 2 right here. All right, so now we multiply this guy by all these, and we get this right here. And now we're going to say this, we're going to say that B nu is equal to all this, right? A contraction over beta, contraction over rho, and we end up with is this single index here. And so to condense this guy, condense this guy here, we use this to get this. This is equation 26. So with all this done, we can now place 26 into our infinitesimal transformation, which again is this guy. We plug that into here, we get this, and we get this now, right? So this tells us something about what B is, right? So B is actually this, right? So when we go back to equation, again, please ignore the dogs. We get, if we go back really quick to, where's the equation I'm looking for? Did not want to be doing this. This guy here, this guy and this guy are related by this, okay? So that's quite interesting. Oh my God, I'm going to kill that dog. All right. So now we have this, we get these guys, and now we have this. This is what we want to see. So our transformation, therefore, is this. Again, my deepest apologies for the dog. So now our transformation is going to be x mu is the new one is going to be the old one plus this. Okay, now we're just doing some manipulations here, right? So we take we can raise and lower indices. So I kind of just lowered or raised index here, but you don't have to, right? So the idea here is that now, okay, so this guy here, right? This is just a Kronecker delta mu nu. That's this guy, and that's why we raise this index. And then same thing here, right? Kronecker delta. So now we have, okay, I'll just keep that there. So now we have this guy. This guy here is, well, what we do again, we do this multiplication by I again, and we get these two guys, or this here, right? 2bx, and then we have this operator, and then same thing here, b right here, right? So the reason we do this again is because we now have x mu and x mu, so we can pull that out, and we get our identity operator plus all of this, and then, excuse me, this thing here again is just a contraction over these dummy indices, and so this guy here then becomes this, right? Because we have our beta alpha, or B alpha comes out here. We have B alpha. So now we have this. And this is what we're looking for. This is the generator that we're looking for that's associated with our this C guy, right? So it's associated with this transformation here as part of the transformation. And this is what's called the special, this is what's called the special conformal transformation generator. This transformation is being the special conformal transformation. All right. We've derived all of these guys. That was a lot of work, but now we can now start constructing our algebra. And what this is going to mean is that we have a series of operators. Think about quantum mechanics for really quickly. Quantum mechanics, we have our operators x, mu, that's our position operator. We have our operator rho, or not rho, our momentum operator, right? Right, so we have x operator and we have a momentum operator. And when we do the quantum mechanics stuff, we can calculate the commutation relationship between the two. And in quantum mechanics, it is, what is it? It's I, h bar, or this is really quantum mechanics. Quantum mechanics is based on this canonical quantization principle. Well, and these things are operators, right? These things are operators. We've showed, so we have our K operator, right? We have our K operator. This is our special conformal operator. We have our rotation operator. We have our dilation operator. And we have our translation operator. All of these guys are going to form an algebra like this, right? So we're going to want to figure out what K with L is. We're going to want to figure out what K with D is, and so forth, right? And so we're going to derive those relationships in the next video. And from that, we'll have a solid foundation for conformal field theory, and we'll be able to propel ourselves forward into talking about more advanced stuff as well. We're going to be able to put this in the context of string theory and phase transitions, topology, and all that good stuff as well. So with that being said, I hope you like this type of content. Make sure to hit the like and subscribe button, and I'll see you guys in the next one. Bye.